differential equation for forced harmonic oscillator. Differential equation for forced harmonic oscillator. Okay. Let f equal to f naught e to the power I omega t. Okay. Be an external periodic force. Be an external periodic force. External periodic force. Okay. And applied to a damped harmonic oscillator. Here f naught as the maximum value of the applied force. Okay. And omega is the angular frequency is applied to the oscillation system. Then the differential equation for motion of force driven harmonic oscillator. Okay. Then driven harmonic driven md square y upon dt square plus r dy by dt plus sy equal to f naught e to the power I omega t. This is the equation number 1. This is complete solution of this equation will consist of two parts. First, transient state. The first part is known as the transient term, which dies away with time. The transient behavior persists only for a short intervals of time. During this time, the natural oscillations of the system will prevail and the system will behave as if no external force is acting. The displacement of the oscillation is therefore given by the solution of the equation md square y upon dt square plus r dy by dt plus sy equal to 0. This is the equation number 2. Dividing equation 2 by m and substituting. Dividing equation 2 by m and substituting. Okay. S by m equal to omega naught square. Okay. Then d square y upon dt square plus 2b dy by dt plus omega naught square y equal to 0. Okay. Omega naught square y equal to 0. The oscillatory solution of this equation is the oscillatory solution of this equation. The oscillatory solution of this equation is y equal to a naught e to the power minus bt sin under root of omega naught square minus b square t plus 5. Okay. Where is a naught e to the power minus bt sin omega dash t plus 5. Okay. That is where omega dash equal to under root of omega naught square minus b square and a naught equal to y naught omega naught whole upon under root of omega naught square minus b square. And tan phi naught equal to under root of omega naught square minus b square by b. The amplitude a naught e to the power minus bt decay with time due to presence of the term equal to minus bt. The quantity omega naught is known as the natural frequency of the oscillator in the absence of dissipative as well as driving force. Dissipative as well as driving force. Okay. The amplitude a naught, the amplitude a naught e to the power minus bt decays with time due to the presence due to the presence of the term e to the power minus bt. The quantity omega naught is known as the natural frequency. 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 Okay? Natural frequency and of the oscillation in the absence of dissipative as well as driving force. Second point, steady state. Okay. Second point, steady state. Okay. Second point, steady state. The second part is known as the steady state term. The second part is known as the steady state term. Known as the steady state term. Okay. The second part is known as the steady state term, which describes the behavior of the oscillator after the transient term has died away. After the transient term has died away. Transient term has died away. Okay. To begin with, both the term condition contribute to the motion of the oscillator, but later on the transient term becomes almost negligible, and the ultimate behavior of the oscillator will be given by the steady state term. During the transient stage, the oscillator neither oscillates with its natural frequency nor with the frequency of the impressed force. During the steady state, the oscillator oscillates with the frequency of the external driving force. The external driving force is a periodic force which may be given by the external driving force. The external driving force is a periodic force which may be given by F equal to F naught cos omega t, or F equal to F naught sin omega t. Okay. Or by a complex quantity F equal to F naught e to the power I omega t equal to F naught cos omega t plus sin I sin omega t. Okay. is a combination of two forces. Is a combination of two forces. Two forces is a combination of two forces. If the external driving force is F naught cos omega t, then it is the real part of the complex quantity. If the driving force, if the driving force of F naught, if the driving force of, if the external driving force, if the driving external force F naught cos omega t, then it is a real part. It is a real part of the complex quantity. It is a real part of the complex quantity. Real part of the complex quantity. Okay, and complex quantity F naught e to the power I omega t. E to the power I omega t. Okay, I omega t. If the force is F naught sine omega t, then it is part of the complex quantity. Then it is part of complex quantity. Then it is part of complex quantity. It is part of complex quantity. Okay, quantity F naught e to the power I omega t, which is preceded by I. F naught I omega t, which is preceded by I, we shall therefore consider a general case of the external force given by F equal to F naught e to the power I omega t, and driving force it is particular case, and derive from it the particular cases, F equal to F naught cos omega t, or F equal to F naught sin omega t. Okay, from the equation first may now be written as md square y upon dt square plus r dy by dt plus sy equal to F naught e to the power I omega t. Okay, this is the equation number third. Okay, in the steady state, let one particular solution of the equation be in the steady state, let one particular solution of the equation be y equal to a e to the power I omega t, where a is the complex quantity, where a is the complex quantity, okay, and dy by dt equal to I omega a e to the power I omega t. Okay, and d square y upon dt square equal to equal to minus omega square a e to the power I omega t. And substituting in equation number 3, we have substituting in equation number 3, we have a minus omega square m plus I omega r plus s e to the power I omega t equal to f naught e to the power I omega t. Okay, this relation is true for all value of t. This relation is true for all values of t. All values of t. Okay, all values of t. So a equal to f naught whole upon I omega r plus s minus omega square m. That is minus I f naught whole upon omega r minus I s minus omega square m. Okay, and that is minus I f naught upon omega r plus I omega m minus s by omega equal to minus I f naught whole upon omega vector z m. Okay, where vector z m is the mechanical impedance, the mechanical impedance. Okay, putting r equal to zm cos omega phi, and omega m minus s by omega equal to zm sin phi, where zm is the modulus of the complex impedance. Zm is the modulus of the complex impedance. Okay, then complex impedance. Okay, putting r equal to zm cos phi and omega m minus s by omega equal to zm sin phi, where zm is modulus of the complex impedance. Okay, complex impedance. Zm, we get vector Zm equal to r plus I omega m minus s by omega equal to zm cos phi plus I zm sin phi. Okay, or zm vector equal to zm e to the power I phi, where zm Zm equal to mod of Zm vector are equal to Zm square cos square phi plus Zm square sin square phi whole to the power 1 by 2, or Zm equal to under root of r square plus omega m minus s by omega whole square. Okay, and tan phi equal to then this is the y-axis, and this is the x-axis. This is the x-axis, x dash, y dash, x dash, y dash. Okay, and this is the angle. Okay, and the angle is if the angle is phi, and this is the impedance Zm, then xm equal to I omega m minus s by omega equal to Zm sin phi, and r equal to Zm cos phi. Okay, real axis. Real axis is this, and this is imaginary axis. Imaginary axis. Okay, then tan phi equal to Zm sin phi upon Zm cos phi equal to omega m minus s by omega upon r, that is xm by r. Okay, phi being the phase difference, phi being the phase difference between displacement y, and applied force F. Okay, that is y equal to a e to the power I omega t equal to I minus I f naught upon omega z bar m e to the power I omega t. Okay, that is minus I f naught upon omega z m e to the power I phi into e to the power I omega t. So this is y equal to I minus I f naught upon omega z m e to the power I omega t minus phi. Okay, let us discuss two cases when f equal to f naught cos omega t and when f equal to f naught sin omega t. We will show that the driving oscillator is always behind the driving force in phase and is explained also as under. Okay, and driving force f equal to f naught cos omega t. First, when driving force f equal to f naught cos omega t, if the external driving force f equal to f naught cos omega t, then it is the real part of the complex function. Then it is the real part. It is the real part of the complex function of the complex function. It is the real part of the complex function f naught e to the power I omega t. Therefore, the steady state term will only consist of the real part of equation number 4. This is the equation number 4, okay? And which may be put in the form y equal to minus I f naught upon omega zm cos omega t minus phi plus I sin omega t minus phi. Okay, that is f naught upon omega zm in bracket minus I cos omega t minus phi plus sin omega t minus phi. Okay, that is minus I f naught upon omega zm cos omega t minus phi plus f naught upon omega zm sin omega t minus phi. Okay, this is the equation number 5, and the real part of the above equation gives, and the real part of the above equation, real part of the above equation gives y equal to f naught upon omega zm sin omega t minus phi, okay, sin omega t minus phi, and y equal to f naught upon omega zm cos omega t minus phi plus pi by 2. Okay, the driving applied force F is F naught cos omega t, which is the real part. Okay, and the driving applied force, the driving applied force is f naught cos omega t, which is the real part of f naught e to the power I omega t equal to f naught cos omega t plus I f naught sin omega t. Comparing y equal to f naught upon omega zm cos omega t minus phi plus pi by 2, and f equal to f naught cos omega t, we find that the total phase difference between the displacement y and the applied force is, we find that the total phase difference between the displacement y and the applied force F is minus phi plus pi by 2. Okay, in the steady state, the amplitude is f naught upon omega zm. Okay, second point, when driving force F equal to, when driving force F equal to F naught sin omega t. When driving force F equal to F naught sin omega t. The external driving force F equal to F naught sin omega t is a part of the complex function. Is a part of the complex function. Part of the complex function. Part of the complex function. Okay? F naught e to the power I omega t, which is multiplied by vector operator I. Therefore, the steady state term will now only consist of that part of equation number 4, which is multiplied by I, which is from the equation number 5. We get y equal to minus f naught upon omega zm cos omega t minus phi. Okay, that is f naught upon omega zm and sin omega t minus phi plus pi by 2. Okay, the driving force F naught sin omega t, comparing the driving force is F naught sin omega t, comparing y equal to F naught upon omega zm sin omega t minus phi plus pi by 2 with f equal to f naught sin omega t. F equal to f naught sin omega t. We again find that the total phase difference between the displacement y and applied force F is a phase difference between the displacement y and applied force F is minus phi plus pi by 2 is the steady in the steady state. In the steady state, the amplitude is also f naught upon omega zm. F naught upon omega zm. Phase difference between driven oscillator and driving force. Okay. Phase difference between driven oscillator and driving force. Driven oscillator and driving force. We have proved above where the driving force when the driving force F equal to F naught cos omega t. F naught cos omega t, the displacement y equal to F naught upon omega zm cos omega t minus phi plus pi by 2, and when F equal to F naught sin omega t, then y equal to F naught upon omega zm. F naught upon omega zm sin omega t minus phi plus pi by 2. Okay. In both the cases, we find that the driving oscillator is always behind the driving force in phase. In both the cases, we find that the driving oscillator oscillator, driven oscillator is always behind the driving force in phase. Is always behind, always behind, always behind the driving force in phase. Behind the driving force, behind the driving force, driving force in phase, in phase. Okay, the value of the difference in phase is minus 5 plus pi by 2. Change in amplitude with frequency of driving force. Okay, change in amplitude with frequency, change in amplitude with a frequency of driving force. When periodic driving force, when periodic driving force, F equal to F naught cos, F equal to F naught cos omega t, F naught cos omega t is applied to damping oscillator and a steady state is reacted. The displacement is given by y equal to F naught upon omega Zm sin omega t minus phi, where y equal to displacement, y equal to displacement. Okay, where Z is the mechanical impedance offered by oscillator and its magnitude is given by Zm equal to under root of r square plus omega m minus s by omega square, where Zm equal to mechanical impedance, okay, and this is offered by the oscillator and its magnitude is Zm equal to under root of r square plus omega minus s by omega. Okay, and tan phi equal to omega m minus s by omega by r. Okay, r is being the damping constant, where r is the damping constant, and m the mass, and m is the mass, and s the stiffness, or spring constant of the oscillator. From the previous article, we proved previous article. Then third A, substituting 2b equal to r by m and omega naught square equal to s by m in, and this is the equation number second, and this is the equation number first. Okay, in second we get Zm equal to m by omega under root of 4b square omega square plus omega square minus omega naught square whole square. Okay, and omega naught being the natural frequency of the oscillator, where omega naught is being the natural frequency of the oscillator. Okay, and y equal to f naught whole upon omega m by omega m by omega under root of 4b square omega square 4b square omega square plus omega square minus omega naught square whole square sin omega t minus phi. Okay, that is y equal to f naught under root of 4b square omega square plus omega square minus omega naught square. Okay, whole square sin omega t minus phi, where f naught equal to small f naught equal to capital F naught by m, capital F naught by m, that is small f naught. Okay, capital F naught by m and tan phi equal to omega m minus s by m by r, that is omega square minus omega naught square whole upon 2b omega. Substituting f naught upon 4b square omega square plus omega square minus omega naught square whole square equal to a. The displacement amplitude we have y equal to a sin omega t minus phi. Y equal to a sin omega t minus phi. Then we shall study the behavior of displacement amplitude versus a driving force frequency in three stages of frequencies: low frequency, resonant frequency and high frequency. Low frequency, resonant frequency and high frequency. Okay, then first, at low driving frequencies, low driving frequencies, omega is less than omega naught. Okay, is that the driving force frequency is very much less than the natural frequency. Okay, is that driving force frequency is very much less than driving force frequency in very much less than the natural frequency omega naught. Natural frequency. Okay, natural frequency of oscillation, the displacement amplitude A equal to f naught whole upon under root of 4b square omega square plus omega square minus omega naught square whole square. Okay, when omega stands to 0, then omega square can be neglected. Okay, omega square can be neglected as compared to omega naught square 4b square omega square as compared to omega naught square whole square, and we get a equal to f naught, a equal to f naught upon omega naught square, that is f naught by m upon s by m is cancelled out by m, that is a f naught by s. Okay, a equal to f naught by s. Okay, thus at low driving force, thus at low driving force frequencies, that at low driving force frequencies, the amplitude of the forced oscillation, the amplitude of the forced oscillations depends upon the driving force, depends upon the driving force f naught, and if stiffness constant, and stiffness constant s, but is independent of frequency, but is independent of frequency, okay. Thus amplitude of force oscillator and also the impedance is stiffness controlled, okay. Thus the amplitude of force oscillator and also the impedance is stiffness controlled, okay. Thus the amplitude of forced oscillator and also the impedance and also the impedance is stiffness controlled, okay. Thus at very low driving force frequency, the amplitude of the force oscillation depends upon the driving force f naught and stiffness constant s, but is independent of a frequency. Okay, thus the amplitude for the oscillator and also the impedance is stiffness controlled. Second point, at high driving force frequencies, at high driving force frequencies, okay, at high driving force of frequencies, that means omega is very much greater than omega naught, okay. If the driving force frequency is very much greater than the natural frequency of the oscillator, for large value of omega square is very much greater than omega naught square, so that omega naught square can be neglected as compared to omega square, and then, okay, then for large value of omega, omega square is very much greater than greater than omega naught square, so that so that omega naught square can be neglected, can be neglected, can be neglected as compared to, as compared to, as compared to, as compared to neglected, as compared to omega square, and then a equal to f naught upon under root of 4b square omega square plus omega square minus omega naught square whole square, that is f naught upon under root of 4b square omega square plus omega to the power 4 equal to f naught upon omega square. Okay, f naught upon omega square, f naught upon omega square. Okay, if b the damping is very small, so that if b the damping is very small, b the damping is very small, so that 4b square omega square can be neglected as compared to omega 4, can be neglected as compared to, omega to the power 4. Okay, as omega is tends to infinite, so a is tends to 0, is that amplitude almost approaches 0, is that the amplitude almost approaches 0, as the driving force frequency becomes very large, as the driving force frequency, amplitude, driving force frequency becomes very large, okay, becomes very large. Third point, frequency displacement resonance. Third condition is very important. Okay, third condition, at frequency of displacement, frequency of displacement, resonance, that means omega equal to omega naught, is that the driving force frequency is equal to the natural frequency of the oscillator. This is the case of amplitude resonance. At this stage, the amplitude is given by a equal to f naught under root of 4b square omega square plus omega square minus omega naught square whole square, that is f naught by 2b omega. Thus, at a driving force frequency equal to the resonance frequency, the maximum amplitude is inversely proportional to damping coefficient B. Amplitude is universally proportional to damping coefficient B. The damping coefficient B for small damping amplitude is large, and for large damping amplitude is small. Okay, thereby for b equal to 0, then a equal to infinite, and b equal to infinite, then a equal to 0. Okay. When, however, damping is present, the displacement resonance takes place at a frequency when however however damping is present damping is present damping is present the displacement resonance 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 take take place take place at a frequency omega equal to under root of omega naught square minus 2b square as proved below. For amplitude A to be maximum, the dA by d omega equal to 0. Now displacement amplitude. Now displacement amplitude A equal to f naught under root of 4b square omega omega naught square whole square. That is d by d omega f naught whole upon under root of 4b square omega square plus omega square minus omega naught square whole square. That is minus f naught 4 omega square minus omega naught square plus 8b square omega. Okay, whole upon 2 4b square omega square plus omega square minus omega naught square whole to the power 3 by 2, that is 0. Okay, then for omega square minus omega naught square plus 8b square omega is 0 r omega square minus omega naught square equal to minus 2b square omega square equal to omega naught square minus 2b square. That is omega equal to under root of omega naught square minus 2b square. That is omega naught under root of 1 minus 2b square upon omega naught square. Omega naught is common. Okay, and omega equal to omega naught under root of 1 minus r square upon 2m square omega naught square. Okay, thus the maximum displacement amplitude or displacement resonance takes place at a frequency slightly less than omega naught, the natural frequency of the oscillator, and is given by then omega equal to under root of omega naught square minus 2b square and that is omega naught under root of 1 minus r square upon 2m square omega naught square. The resonant frequency of driving force omega is slightly less than the natural frequency, slightly less than the natural frequency, natural frequency of displacement omega naught, of displacement displacement of omega naught. Okay. Next, maximum value of displacement amplitude. Maximum value of displacement amplitude. Maximum value of displacement amplitude. Okay. Then amplitude A equal to f naught upon under root of 4b square omega square minus omega naught square whole square. Okay. The displacement amplitude is maximum at frequency of resonance omega equal to under root of omega naught square minus 2b square. Okay. Substituting this value of omega in the expression for we have a max if a max equal to f naught whole upon 4b square omega naught square minus 2b square plus omega naught square minus 2b square minus omega naught square whole square. Okay. Then a max equal to f naught upon under root of 4b square omega naught square minus 2b square plus 4b square. Okay. That is f naught upon 2b under root of omega naught square minus b square. Okay. That is a max equal to f naught whole upon r by m under root of omega naught square minus r square by 4m square. That is f naught upon r under root of omega naught square minus r square by 4m square. Okay. That is f naught upon r omega dash, where omega dash equal to under root of omega naught square minus r square by 4m square. That is under root of s by m minus r square by 4m square. That is natural frequency of damped oscillator. Natural frequency of damped oscillator. Okay. Graphical representation. Okay. We have seen that amplitude of force vibration at low frequency is f naught by s. Low frequency for low frequency when we have seen that amplitude of force vibration at low frequency A equal to f naught by s. Okay. And almost becomes zero at very high frequency, and if frequency is very very high, then amplitude is zero. Amplitude approx 0. Okay. 0 and becomes 0 the maximum value of displacement amplitude A max and A max equal to F naught by R omega. F naught by R omega dash. Thus, higher damping, smaller is the amplitude at resonance as shown in the figure. You can show okay. This is R1 and this is R2. This is R2 and R1 is the greater than R2. R1 is the greater than R2. Okay. The amplitude Max equal to F naught by R omega dash. R omega dash F naught equal to Max equal to F naught upon R omega dash. Thus, higher the damping, smaller is the amplitude. Higher the damping, smaller is the amplitude. Smaller is the amplitude. If the damping is higher, then amplitude is smaller. At a resonance as shown in the figure, R1 is the greater than R2. R1 is the greater than R2. The value of Max correspond to R1. Max correspond to R1 is less than that of correspond to R2. Okay. The frequency for maximum displacement resonance. Maximum displacement resonance. The frequency for maximum displacement resonance omega dash equal to under root of omega naught square minus R square by 4 m square. R square by 4 m square. R square by 4 m square. Hence, as R decreases, omega dash comes closer to omega naught. R decreases, omega dash comes to closer to omega naught. And as compared to Max correspond to R1. Compared to Max correspond to R1. Correspond to R1. Okay. Correspond to R1 and R1 is the greater than R2 and when the frequency and corresponding to R1 and when the frequency of external periodic force is equal to the natural frequency of the body. The external periodic force helps to increase the amplitude of vibration of the body at each step, as the external applied force is always in phase with the vibration of the body. Every new impulses adds to effect of all the previous impulses, as the successive impulses always arrive in the phase, and the accumulated effect is to make the body vibrate with a large amplitude, resulting into resonance. Okay. Next is in comparison of natural frequency and displacement resonance frequency.